Okay, calculus, we are looking at AB 29 Fundamental Theorem of Calculus, Part 1. This is probably the favorite thing to do in integration. It's the kind of key skill when it comes to integration. We're about to combine something that we did earlier when we saw this symbol, dealing with the antiderivative. And now we're going to involve these pieces here. So let's pieces in those calculations. Okay, on your calculator, graph y equals 2x. I got a calculator. Hopefully you have a calculator too. I'm going to go to y equals here. I'm going to delete these old ones. We're going to put some brand new ones in here. So my screen looks like that. I'll go to my y1. I'm going to put in 2x. And we're doing it over the interval 0 to 6. So I need to go from 0 to 6, which really means this could go from like 0 to 20 or even 15. Let's do 0 to 16. And for our y scale, we'll do it by ones. Okay, so there's my graph. Enough. Looks kind of like this. So right here, this goes all the way to 12. This goes out to 6. Here's 0, 1, 2, 3, 4, 5, and we're counting up here 1, 2, 3, 4, 5, 6. Let's give ourselves a halfway point. So let's calculate this. We did this kind of before. This is the accumulation function from 0 to x, and if we're trying to calculate area with a capital F here, what is the area from 0 to 0? Well, that's a nothing area because we don't move at all. 0 width and 0 height, actually. So that equals 0. Let's do the next one. How about blue here? So now I'm going out to this first triangle. I have a width of 1, but a height of 2. So that's 1 times 2, then divided by 2, and that's going to be 1. Now if I go all the way out to the red line here at f of capital F of 2, this is going to take me all the way up to 4. So the area of that triangle is 2 times 4 divided by 2, and that's really 4. Alright, we're doing okay here. What's the next one? The next one, let's do in purple. We're going to go all the way out to 3, and this takes me up to 6. So the area of this triangle is going to be 3 times 6, which is 18, but it's a triangle, so I divide it by 2. That's 9. Okay, that's not too bad. Let's keep going. How about some maroon here? So we're going to go all the way out to 4, and this is double that height, so now I'm looking at a height of 8. And so 4 times 8 is 32, but then I got to divide that by 2, and I got 16. Does anybody see a pattern? Ooh, this is interesting. I think I see it. Can you? Let's try and see if we can find it. So now we're going all the way out to 5, which means that this value that we are getting to here is 10, and out to 10, so 5 times 10 is 50, split it by 2, you get 25. And then the last one, we'll do there in an olive green, goes all the way out to 12. We got this vertical of 12 by 6, 12 times 6 is 72, divide that by 2, we got 36. Do you guys see anything? What's the relationship between x and f of x? Hopefully you see it. Capital F of x equals x squared. So in other words, capital F of, let's pick a different number. How about capital F of, I don't know, 10 would be 10 squared, or 100. So if we went all the way out to 10, the area would be 100. All right. Then that kind of appears that it has a lot to do with this antiderivative. We look at here, we got 2t, and that's just going to be x squared, or it could have been t squared, depending on what values we assign here. Really, I mean that's all that's saying. But we could have said too, and this is kind of where we're going to go, is what's that relationship between this function and its antiderivative and this, and then how do these two pieces tie into that as well? So let's break that down. We got some trig that we can do too, and we're going to use a fancy function. It's this one right here. So honestly, that is really all that you're going to need for this next thing that we do. This has some fancy, crazy stuff going on where we're supposed to, like do a scatter plot and then plot it point by point. We're going to plot a whole bunch of points, 1,000-ish points. All right. So I'm going to go to my y equals. I'm going to clear that. I'm going to put in here. Actually, no, I will put in here. I'll put 2x. We'll leave that in there. But for this next one, I need capital F, little n, capital I, little nt. So that's function int. In other words, function integration. That's under the math menu. So if we go to math, I need to find where do I have f in int. That would be at the bottom here. It's actually little f in int. It's number 9 on mine. It might be something different for you, but I see it as number 9. So press 9. Okay, so what do I type in next? It looks like I type in y1. So that means I got to go to my vars menu, my variables, then over to y vars, click on function, and y1. And then I got to put a comma. Where's the comma? It's right here next to the parentheses. So I'm going to click comma, and then x, and then a 0, and then another, whoops, wait, I forgot my comma. Comma, 0, comma, x. Okay, so we just did that. So now we put that information in there. So let's see what we got. Now it says I can go to second and then table, and it's asking me to look at a table. And here's my values. I don't even have to do the table. It actually calculated those areas of the accumulation function for me. Now my table set, I'm going to start that at 0 and go up to 2 pi. So 0 and the delta on the table, let's do delta, how about pi over 2, I guess. So we got second pi divided by 2. There we go. So now when I look at my table, here's my values that I'm getting. And notice that this is 0, pi over 2, pi, 3 pi over 2, 2 pi, and so on. Well, we're only going to, this says from 0 to 6. So now we're going to go from about 0 to 2 pi. And, oh, but we need to calculate cosine. So I needed to put cosine in there. Whoops, not hard to fix. So I go to y equals, and where it says 2x, I don't have to do anything else. I can just put cosine of x. Let's close off those parentheses. All right, now we're in business. Whoops, we need more window, because our window goes from 0 to 2 pi. Let's click on the window here. Is it still calculating? Oh, all right, I just pulled a little trick there. I don't know if you guys know what I did. It's making a lot of calculation. It's drawing this really slow. And it's still drawing this. That's what these little bars up here mean. It says processing, thinking, buffering, da-da-da-da-da-da-da. Still drawing, waiting, waiting, waiting. We're still waiting here. All right, it's done. Okay, so I need to go back to my window. I'm going to go from 0 this time all the way to 2 pi. So I do 2, then press second, and then pi. So it's going to calculate that for me. 6.2831853, da-da-da-da-da-da. And for the y minimum, let's just keep it between -1 and 1, because that's where most of these sine, cosine, trig graphs go. All right, so there's cosine of x. Cool. Now here's the other one, and it's going to draw it for me nice and slow. So I'm gonna see what's happening here, and it's just going. It's drawing it. It's because it's got to calculate it piece by piece, and it's literally calculating probably, I would say, 100 times in here. But if you look at that, that looks like a familiar function too. In fact, pretty common, a lot like cosine. So this is where it gets really interesting. I took the accumulation function, but instead of like an algebraic function in there, we put in cosine, a trig function. So if I were to stretch this to fit the same window that you guys have, that's what we have there. Okay, I can even fade this out a little bit, and hey, that looks pretty much right on. I need to pull this over, about there, about there. That looks like it's about right. There we go. So we have this cosine function that we said, here's cosine. This is cosine of x. But then what's this one? It's a mystery. Actually, hopefully by this point, with all my teasing, I hope you guys are starting to see that it's sine of x. It starts here at 0, it goes up, it crosses here at pi, it goes down, and then it comes back at 2 pi. That's sine of x. So what does this mean? This means that capital F of x, if this were the accumulation function with cosine t, is really sine of x. The antiderivative of cosine is sine. We kind of knew that. Kinda. We did review some stuff with that. So now we're going to be talking about this idea, a connection between area and indefinite integration, which was this right here. This was our antiderivative. So if capital F is the antiderivative of little f, then this thing right here, all we got to do is figure out what's that antiderivative and plug in these two numbers. We're going to take the top minus the bottom. So what does that mean? It's right here. Look at this first one. If we're trying to find the definite integration, notice that we have a 1 at the start, a 2 at the finish, and we're finding the area under x squared. We don't have to actually use geometry. Now we can jump into calculus. We know the antiderivative of x squared. It is x cubed over 3. And here's some notation for you. Now that we took the antiderivative, we're going to change this curly line into a straight line. But we're going to evaluate it from 2 and then subtract at 1. So in other words, that means we're going to have 2 cubed over 3 minus 1 cubed over 3. That's very interesting. So this would be 8/3 minus 1/3, which gives me 7/3. Done. That's it. Now maybe you're wondering, is that for real? Is that exactly what it is? Well, I hope that you guys remember that your graphing calculator can, and it can actually calculate area under a curve. So let's do that. Looks like the video is finished converting there. Let's do that with this piece here. We're going to set y1 equal to x squared. And for our window, we're just looking from 1 to 2. So let's go from 0 to 2. And we need to go from like 0 to, I don't know, 4, 5. That looks good. So here's our graph. There's our function right there. So we want the area right in here between 1 and 2. And that's not easy to do geometrically. But our calculator can help us with it. And we just did it with some calculus. But let's confirm it. So what's happening then is I'm going to take the area. So I need to go to second and calculate. The area, look at that curve, little f of x, number 7. So I need to find the area under the curve. What's my lower limit? It's 1. That's where I start. Where do I finish? I finish at 2. Boom. The area is about 2.333333. So let's confirm that that's what we actually got. Whoops. There we go. Yeah, I think it is. 7/3, 2 1/3, same thing. So we're getting the same thing as a calculator. Who needs calculators? Alright, so now we got to do the same thing, but just more complex algebra. No big deal. Antiderivatives. Do each antiderivative individually because all we're doing is adding or subtracting, so we can split it up into multiple problems. The first antiderivative. What's the antiderivative of 3x squared? Well, let's do this maybe in a different color here. How about purple? This is going to become 3x cubed over 3. Remember, you add 1 to the power and divide by it as well. Next is going to be minus 2x squared over 2, and then minus 1x. We're going to be evaluating that from -1 all the way up to 3. So how do I run through that process? Well, I can simplify a little bit here. These 3's, these 2's, those simplify to just 1. So I have x cubed minus x squared minus 1x. So I'm going to have 3 cubed minus 3 squared minus 3. If I plug in, here's capital F of 3, where F, capital, is the antiderivative, minus, then I got to figure out what's capital F of -1. Well, now I got to plug in -1 for each of those. So I'm going to have -1 cubed minus -1 squared, and then minus -1. Oh, lots of calculation here. Let's give ourselves just a little bit more space. So 3 cubed, that's 27. 3 squared, that's 9. 3, that's 3. Okay, so that's our first group. Our second group, -1 cubed is -1. -1 squared is 1. And -1 is +1. Okay, so the first group we got 27 minus 12, which would give me 15. Minus, the second group is at -1, -1, +1, so that's -1. All total, 16. That's our answer. Okay, let's do this next one. We're looking for the area under the curve from 0 to 9 of x, and we got a square root here. So what we want to do first is, we're looking for the antiderivative, which we're going to see is really capital F. That's how we're going to antiderive and then get to F. And then we're going to find F of the top, and we're going to subtract F of the bottom. You guys are probably wondering, what? Why do we have this top minus bottom and all that kind of stuff? Right now, let's just build it as a mechanical skill, but we're actually going to look into this a little bit later and see why does that work. All right, so let's start. We'll do this in like a brownish red here. So this is really x to the 1/2. And by rewriting it as a fractional power, that makes it a little bit easier for us to do the antiderivative. So we're going to add 1 to 1/2, which is 3/2. So that becomes x to the 3/2 over 3/2. Or 2/3 x to the 3/2. Alright, so let's calculate this at 9 and 0, because we're doing from 0 to 9. So that's 2/3 of 9 to the 3/2 minus 2/3 of 0 to the 3/2. Well, 0 to the 3/2 power, that's pretty easy. That's just 0. And this 2/3 times that is 0. So I really need to look at the first one. So 3/2 means two things. That means really square root of 9 and cubed. And we can do that square root and cubed in either order. I think we should square root first, because square root of 9 is really 3. So this is 2/3 times 3 cubed. Well, I could cancel this 3 as well, but let's just kind of keep it simple here. 3 cubed is 27, divided by 3 is 9, times 2 is 18. Whew, lots of pre-algebra evaluation there, but we got it. No big deal. Now let's say I wanted to check these answers. Now I can use a calculator for that, and I just want to show you how pretty much easy it is. So the next function, it was not as simple as x squared. It was 3x squared. So we got 3x squared minus 2x minus 1. And now we're going our intervals from -1 to 3. So I need to make sure that I have -1 to 3. -1. And we're going to go all the way up to 3. I'm going to go all the way up to 10. And we're going to go from 0 to 10. Let's see how that works for us. Okay, so we go off the screen, way off the screen. So let's talk about this area from -1 to 3. So the area from -1 to 3. That means that I'm going to do second, calculate. The area is 7. Lower limit, -1. Upper limit, 3. 16. Like magic, we are calculators. Like I said, if we're getting the same answer as a calculator, that's some good stuff. Let's do the same thing now for the last one just to check our work here. So now our function is not as long, but still it was a little complex. It was x to the 1/2, or square root of x. So I can do second square root of x. Alright, that's in there. And now I'm going from 0 to 9. So I'm going to go to my graph. I'm going to do second, calculate. The area is number 7 again here for me. My lower limit is 0. That's where I start. My upper limit, where do I finish? I finish at 9. And the area is 18. Now this says 18.000045. And you're probably wondering, what? How come I got 18 and it got 18.000045? Well, here's why. If you guys remember back to when we were doing Riemann sums with boxes and trapezoids and all that kind of stuff, those are approximations. And the skinnier we make those approximations, the narrower we make each interval, we were getting really close to the actual area because we could follow the curvature of the line. Your calculator, all it's doing is making really skinny boxes, like skinnier than this line that I can draw. And it's doing thousands of them, and it adds them all up. All those boxes, it adds up. Same thing for this one. It's adding up all these values, and then it just takes that total sum. So right here, it added up an extra 0.000045. And that's an approximation. So you want to keep that in mind. The actual answer was 18. Let's continue this practice. We're going to speed up here just a little bit, kind of get in the swing of things, you could say. Alright, so I want to look at this, but I want to do some rewriting. We got a constant here, 2/3, and the x squared on the bottom. So this is going to be the integral from 5 to 10, or the area under the curve from 5 to 10, of 2/3 times x to the -2 dx. Okay, so first thing I need to do is find the antiderivative of x to the -2. So I'm going to add 1 to the power. That becomes x to the -1. Then I can divide by that number as well. So I'm dividing by -1. Then I got this 2/3. And we're evaluating this from 5 to 10. So now to kind of split that up, I'm going to have 2/3 times -1 over x, and that's from 5 to 10, which is really 2/3 times -1 over 10 minus 2/3 times -1 over 5. So if I were to simplify this, I got -2 over 30 minus, now the next one here is minus, so that's plus 2 over 15. Now something that's kind of interesting, 2 and 30 would simplify to 1 and 15. So -1 over 15 plus 2 over 15 equals 1 over 15. Conveniently. Alright, next. We could do some u substitution for this, but that's more advanced than what we really need to do. It's actually more convenient for us if we just do some algebra with this 2x minus 1, some box multiplication. So we're going to do some box multiplying here. We got 2x minus 1, 2x minus 1. That gives me 4x squared. Then we got two of these minus 2x's. And then a plus 1. So I'm going to have the integral from negative 1 to 1 of 4x squared minus 4x plus 1. Now remember, because we're just adding or subtracting each of those terms, not multiplying or dividing, but adding or subtracting, that means that we can separate it into 3 different problems. So we're going to do the antiderivative of the first one, antiderivative of the second one, antiderivative of the third one. So what's the antiderivative of the first one? Well, that's going to be the constant's 4, and the x squared becomes x cubed over 3. The next one, we have a constant 4, but this time it's going to become x to the first power changes to x squared over 2. And then the next one after that, it's a constant of 1, but a constant is going to become constant times x. Now we're evaluating this from negative 1 to 1. So I'm going to have 4/3 times negative 1 cubed minus 4 times negative, or 4 halves. What's that really? That would be 2 over 1. So I guess I could simplify that. Let's do that. So this is 2 times negative 1 squared. And then for the next one, we got plus 1 times negative 1. Now you might want to be saying to yourself, so you're like, I wish I could just simplify this more. Well, maybe we can. This would become negative 4/3. How did I get that so fast? Negative 1 cubed is negative 1. Negative 1 times 4/3 is negative 4/3. Easy. Plus 2 and then minus 1. Okay? So that's my first group. Let's start on the second group before we get too far ahead of ourselves. This second group here is going to be 4/3 times 1 cubed. Oh, we totally did this backwards. Oh my goodness. Oh my goodness. Notice that I did the bottom one first. I went backwards. That means that this is going to be the negative, and I got to subtract the other group in front of that. So let's go ahead and do that. Let's put it in front of it, just to kind of keep it standard. But this will be easier calculations. We're talking 4/3 times 1 cubed, or 4/3. 2 is minus 2 times 1 squared, which is just 1. And then plus 1 times 1, which is 1. Okay. So watch what happens. We can start simplifying. This negative 2 and plus 1 would be a minus 1. This plus 2 and this minus 1 would be a, what's that going to be? That's going to be a plus 1. So we have negative 1 minus 1. That equals negative 2. Now let's do the fractions. What's 4/3 minus negative 4/3? So that's really a plus because it's minus minus. That's going to be 8/3. Now I could do more simplifying, but that's enough there, actually. So I'd have 8/3 minus 2. My goodness. Craziness. We need a new color before our eyes go crazy. Let's do blue. Alright, so I got this integral here. So much stuff happening. Multiple numerators, individual denominator means I can split it up into multiple fractions. So I'm going to have x over cubed root of x, which I'm going to go ahead and rewrite, because cubed root of x is really x to the 1/3. So this is x to the 1/3. And then we got minus 2 over x to the 1/3. And of course dx all times this. We're going from 1 to 8. So this first term, x to the 1 over x to the 1/3, that would simplify to x to the positive 2/3 because you subtract the powers there. Is the shortcut I'm using. Then we got minus 2x to the negative 1/3. So I'm still doing the same integral, haven't really changed anything, and just manipulated some of the algebra. So now we're looking at this in x to the 2/3. We got to add 1 to that. That would be 5/3. So we got x to the 5/3. Then minus 2, negative 1/3 plus 1 is going to be 2/3. So it's minus 2x to the 2/3. And then we're evaluating that from 1 to 8. Okay. Now remember, when you have a fractional power, that means that this first one is really going to be third root and then fifth power. And the second one is going to be minus 2. We still got third root and now second power. So we're going to have, for our first group, we have 8 third root of 8 to the fifth power, which is really 2 to the fifth. Then we got minus 2 times the third root of 1 and then 1 squared. Oh, not 1, 8, pardon me, which is really 2, and then 2 squared is there. So it's 2 to the fifth minus 2 times 2 squared. Lots of algebra, lots of steps here. So just for the first half, we got that. For the second half, can I move this down? No, I can't. It's all connected. That's okay. So that's going to be 32. Is that 32? Yeah, 8, 16, 32. So 32 minus 8, so that's 24 for that first half. But then what's the second half? Let's do the second half in red, the bottom part, because I think that's going to be a little bit easier. I'm going to have 1 to the 5/3 power, which is really just 1, and then minus 2 times 1, which is really negative 1. So that's actually not as hard as I was thinking. So now put that together, minus minus makes a plus, we got 25. Now I'm a little unsure about that. I'm actually quite unsure because there's so many places I could have made a mistake. I would like to check with my calculator, so I'm going to do that. I'm going to pull that up here. I'm going to go to my y equals, and I need to put in this new function. So this new function, it's got a numerator. The numerator is x minus 2. And then the denominator, we got some action going on here, is x to the 1/3 power. So it's x to the, and I got to put that 1/3 in parentheses here, x to the 1 divided by 3. Close it off again. So there's my function. Let's see if I can calculate this area. Now we're going from 1 till, what is it? 1 till about 8. So I need to do second, calculate. We're doing the area. In this case, I have it listed as number 7. And my lower limit is 1. My upper limit is 8. What does it come up with? 9.6. Did we make, what are we looking at? Where are we making mistakes? X to the 2/3 changes x to the 5/3. That's x to the 5th cubed root 2 to the 5th. And then here we got 2. Oh, wait, no, that's fine. Minus 2 over x to the 1/3 is x to the negative thirds, 2/3. Wow, I'm really struggling here because I can't see where my mistake is. Let's see if I plugged it in correctly here. So if we go back to y equals, we got x minus 2 divided by, and then all of that, x to the 1/3. We're taking the area, took the area from 1 to 8, it looks like. You know, I got some of this down in the negative. Maybe that's off a little bit. But that kind of makes sense. That's a negative area. So we got minus negative 1. Let's just do the area from 2. Where does this cross right here? Where does that cross? It crosses at 2. So let's do the area from 2 to 8. So I'm going to do second, calculate. The area, which is 7. My lower one is 2. My upper one is 8. That gives me 10.05. I'm getting something way off here that's not even close to these numbers. So either I'm doing something wrong in the calculator with the way I typed in the function, or I did something wrong in the algebra. I'll have to go take another look at this. But this is why you got to check. Now you're never quite sure if that's exactly what you should be getting. So let's try this real quick. We're going to split this up into two terms. So it's going to be x to the 2/3. Oops, x to the 2/3. So that's x to the 2/3 minus 2 times x to the negative 1/3 Let's see if our graph looks the same. Actually, it does. It looks very much the same. So let me see if I can calculate the area of that, see if what we're missing is somewhere in there. So I'm going to do second, calculate the area is number 7. Our lower limit is 1. Our upper limit is 8. 9.6. Okay, so there's got to be something wrong in the algebra here, and just somewhere in the middle in the steps if we're going from 1 to 8. Not sure where it is. We got, let's see, 8 third root is 2, 2 squared is 4, 4 times 2 is 8, 2 to the 5th is 32, because that's cubed root of 8 is 2, 2 to the 5th, we got 5/3. Yeah, something's way off here. But you know what? That's okay. We'll just have to go back and check our answers. So I probably already annotated this. So I put the answer in here, I'm sure. And I'm even going to try and plug this into Wolfram Alpha and see if I can get it there. All right, so these last three here, we got those three and then one more page at the end, just as a quick reminder. So we're just going to finish up with these last three. So remember, we're just talking about antiderivatives. So for part number 7, we got from 0 to pi and 2 and sine x. So let's take the antiderivatives, each of these. What's the antiderivative of 2? It's really 2x. What's the antiderivative of sine of x? Well, the derivative of cosine is sine, but negative. So because there's not a negative there, that means that this side needs to be negative, and that would have been positive. So it's going to be negative cosine of x. This would be 2x minus cosine of x. And we're going to be evaluating this from 0 to pi. So let's start by plugging in pi. That means we'll have 2 pi minus cosine pi and then we're going to subtract from that by plugging in 0. So it's going to be 2 times 0 minus cosine 0. Okay, so the first one, cosine of pi is negative 1. So this is really 2 pi minus negative 1. And then for the next one, 2 times 0 is 0. Then we got negative cosine 0, which is also negative, but cosine 0 is 1. Right, so now we got a negative negative 1. That's going to be plus 1. So we got 2 pi plus 1 and then plus another 1. So that's 2 pi plus 2. Check. Let's look at this next one. We'll finish it here in maroon. Actually, we're doing a couple of these. Let's keep on moving here. 4x. Well, that constant's going to stay there, but that x to the first power becomes x squared over 2 when you take the antiderivative. Secant squared. So in other words, the derivative of what is secant squared? I'm pretty sure it's tangent, and yeah, it is. So that means that this is going to become plus tangent of x. We're going to be evaluating it from 0 to pi over 4. One note, we could simplify this 4 and 2, and that's going to give us 2x squared. So we're going to have 2 times pi over 4 squared. That's kind of a weird thing to do. We haven't really done that before. Plus tangent pi over 4. So that's our first group by evaluating the top. Now we got to subtract the bottom. So it's going to be 2 times 0 squared plus tangent of 0. Okay, 2 times 0 squared is 0. Tangent of 0 is 0. So this whole second half is gone. But for the first part, let's calculate that a little bit further. We're going to have the pi squared And then we got 4 squared is 16, so it's 2 over 16. We can simplify that a little bit. Tangent of pi over 4 is just 1. So in reality, this is going to be pi squared over 8 plus 1. Excellent. Well, all we got is number 9, and we are done dizzle for the rizzle. Let's get it done. So we got the area from 0 to 5 of 4 minus 2x inside an absolute value. Okay, so something interesting is happening here with this 4 minus 2x absolute value. Let's draw a picture of it. We're going from 0 to 5. If I were to plug in 0 in there, I actually have all the way up here at 4. And this is it's a linear function, and it's got a slope of -2. So then we go down 2 over 1. So we're at 1, and then 2, 3, 4, 5. So then we hit here. But absolute value makes that v. So it's going to go here and then all the way up to about 6. And we get out to 5. So in reality, I could just do this with geometry, and that would be easier than dealing with this absolute value. And a lot of the problem with the absolute value is that it's got two functions. It's a piecewise function. It's 4 minus 2x when x is less than or equal to 2, and then it's negative that when x is greater than 2. So the second line is here, and the first line is there. That's what the absolute value does. It just takes the negative version of the linear function. It's a piecewise. But I'm just going to use some geometry here because I like geometry. So the first triangle, it's 4 high by 2 wide. So 2 times 4 divided by 2. And then for the second triangle, it's 3 wide by 6 high. So 3 times 6 is 18 divided by 2. So 3 times 6 divided by 2. We add that together. This is really 4 plus 9, which is 13. Boom. There we go. Okay, not too hard to do these calculations. I am going to take a look at that number 6 and see what is going on. Where are we going wrong with it? And why are we getting different values? I'm sure it's just somewhere in the middle, messing up the numbers, forgetting some... oh! My goodness. You guys are probably shouting so loud, Mr. Butler, you're such an idiot. It's because this first one's supposed to be divided by 5/3, and this second one's supposed to be divided by 2/3, because when you do the power on top that you change, you also got to divide by that same number. So I'm going to do it right now, but correctly. Insert page after. So here we go. I'm going to take a snapshot of this and put it to my clipboard, and now we're going to paste it to this page. Alright, let's wrap this one up. Wow, I can't believe it took that long to notice the error. So we did the antiderivative, and just so you guys know like where we got to it, this part was correct, but I forgot the denominator in there, which means that this should have said x to the 5/3 over 5/3. And then over here we had minus 2x to the 2/3, but that's got to be over 2/3. And we're evaluating that from 1 to 8. So let's go through, calculate some of this. This first one, I can flip these two denominators as fractions, and it's going to become 3/5 x to the 5/3 minus, we got 2 times 3/2, so those 2's are going to cancel each other, times x to the 2/3. Now we did the calculations with x to the 5/3 and x to the 2/3, so I'm not going to repeat those. This is going to be 3/5 times 8 to the 5/3 minus 3 times 8 to the 2/3. So in other words, we did the whole top But now we're going to subtract the bottom, which would have been 3/5 times 1 to whatever power. It doesn't really matter because we know that's going to be 1. Minus 3 times 1. Okay, a couple of quick notes here. 8 to the 2/3 was really 2 squared 4, so that's 3 times 4. And then we still got this 3 times 1. And I'm not going to simplify a whole lot because this 3/5 and this 3/5 will actually help me combine like terms there because they both have a denominator of 5. 8 to the 5/3 we figured out was 24. So that means that we have 3/5 times 24 minus, now this is a 12, and then over here on the second half we're going to have minus 3/5 minus 3. Okay, let's simplify even more. 3/5 times 24, that's really 3 times 24 is 72. So we got 72 over 5. We got a negative 12. We got 3 over 5, but subtracted. And this negative is really going to make a positive, so that's plus 3. So altogether, 72 minus 3, that's 6. 9 divided by 5, negative 12 plus 3 is minus 9. Now if I were to kind of change that into fifths, that's really 45 over 5. So let's see what we would get. We'd have 69 minus 45. 69 minus 45 is going to be 24. No, what are we getting there? 24 divided by 5. Something's missing. Now I think I'm even more off than I was before. Oh, because this other one is, no, that's right. What are we missing here? 3/5, negative 3. Alright, so I got to look at it even further, but this is closer. So, but that is pretty sure, I'm pretty sure this is the mistake I was making, but maybe I'm still making a numerical mistake down here. Alright, so we'll answer this in class, I'm pretty sure. Let's see if you guys can find the error. Ready, set, go. Have a good day.